talk about a faster load balancer than Google's MATLAB. Even though Google's MATLAB is very new, they have already overtaken Google's MATLAB. That sounds really good and not a Flores rules. Hello everyone, I'm from UCloud and I'm from IaaS cloud computing platform. We provide public cloud. Have you used public cloud? You are from all different industries and you are excellent DPDK developers and you probably did some work with public cloud, but actually for the public cloud as an industry, it is different from other industries or businesses. Today, I'd like to take this opportunity to share with you some of our ideas about what challenges we may face as an industry, that is, public cloud, and how we have been dealing with the challenges. We have learned our lessons and accumulated some experiences. These are our modest ideas, and hopefully we can spark up more conversations and ideas to build a stronger community of DPDK. At my company, UCloud, we use DPDK to develop all sorts of applications like marginal routers and gateways and so on. And Vortex was something we launched only in April. And at ASDI in March or April, Google also released a load balancer, which was a coincidence, and we noticed that their design was very similar to ours. So today we use Vortex as an example about some of the issues we have encountered in the public cloud sector and how we deal with these problems in terms of development, operation, and maintenance, what lessons and experiences we have learned. So we have to first look at the background of UCloud. Do you know who the biggest public cloud provider in China? That's Alibaba. Alibaba ranks top 3 in the world. But do you know who number 2, number 3, and number 4 public cloud providers are in China? I don't know yet, because Tencent and Kingsoft are about as big as each other, and also UCloud. We have about 10 data centers. We have 10 data centers worldwide, and every data center has a few thousand servers, and we serve tens of thousands of business or corporate clients. And the biggest challenge for us is size. In terms of the size, we are bigger than most of our corporate clients, and we are bigger than average IT firms. However, compared with telecom industry, our data flow, our traffic is not so high. However, we have our specialty. That is, we have multi-tenants, and we have the overlay structure, which is different from the telecommunication industry. And for Vortex, UCloud,
feature perspective, it is similar to IaaS does. It's just a load balancing software. What's crucial is its scale. We are more focusing on the public cloud, handling the several tens of gigabytes of Ethernet, etc. We also have tens of thousands of users. And we also have an overlay network. All of these coming together is very much different. So first of all, we need to have LVS. In order to have multi-tenants, we will need to have one namespace for each tenant. So among the different tenants, they can use the same IP address. That is also okay. Since it is overlay network, we will need to have OVS to do the packaging and de-packaging, etc. We will also have the virtual net card to have the LVS namespace, LVS to be connected. But everything of the above in Vortex, you just need to use DPDK to do it from step to the beginning. Regarding the actual development, it's just several people working 2 months. It doesn't that long. Of course, we studied a lot from LVS, particularly the connector tracking, etc. Besides, under user space, it has great advantages. The customization is very simple. We have HRW algorithms that was not with LVS. If you need to develop plugin for LVS, you need to write module in kernel. But for user space, if you use DPDK, everything can become really simple. Of course, we also have the standby mode backends. With user space development, it is much simpler than in kernel space. Another advantage is its performance is much better than LVS. For LVS, generally speaking, one core is around 1 megabytes PPS. For one machine, it is around 4 megabytes PPS, but plus OVS. And then, if you have the overlay packaging, the performance will be even more reduced. If you use DPDK to completely develop it, even in the poor 4-core physical server, we can have a 64 bytes line rate already, and for GPS we can have around 200K. So it is much better performance enhancement than the others. Talking about the concurrent connections, there is no upper limits. These are our comparison than Google Maglev. We haven't done a lot of tests, but all of these data are from Maglev papers. The right-hand side column are Vortex performance. To be humble, because Maglev was designed a long time ago in 2008. They started to do the research and development already. Back then, DPDK is not even open source, so Google were using their own bypass techniques to realize Maglev. So the performance is slightly lower than DPDK. On single core, it is around 3 megabytes PPS. In comparison, Linux is 1 Mbps. For one core of us, we can deliver 4 megabytes. With the 4 cores, we can achieve the 16 Mbps already. Next, I would like to talk about how to put them into implementation. We have added saying, for the happy family, the happiness are the same, but for the unhealthy family, they have all different reasons. For us, it is for the same purpose. For the single machine, we have the share nothing structure. Physical card is doing IaaS. For the virtual card and tab device, we are achieving the remote queue. Each core will have its own table. It is a very simple design. Using such an easy structure, we will be able to achieve really nice performance. Horizontally, for extension, we are doing the same thing as Google. We have the ECMP cluster to realize horizontal scale-out. Even for the lowest switch machine, we can have 16 servers to do ECMP cluster already. And to be better, we can have 32 servers to be the cluster. Next slide is even more simple. It is introduction to our ECMP cluster implementation methodology. At the very bottom, it is Linux program BTBD to do the dynamic router. For BTBD, when it communicates with the switch, I need to send a ARP message. The ARP will be forwarded to type device, and the ARP message will be searched. Based on physical drive, it will be sent through DPDK. Regarding the router, it will respond to the response. When ARP receives the message, since it is an ARP message, through type device, it will be transformed to Quokka BGPD. Then Quokka will send the link of TCP DP. It will also read the message and the link through DPDK driver and have it forwarded. The vice versa is very interesting. It also starts from DPDK driver. It will check the destined IP. If it is an IP of type device, it will be transferred from type device directly. The whole BGPD interaction is bypassed to Quokka BGPD. In our network, we are using overlay capsule. So for the overlay packaging, it will automatically be forwarded as well. Using such a method, we don't have to do much. We just take advantage of a corner space Quokka, so we can realize the ECMP cluster very efficiently. This is another fact which is very interesting. Since our Vortex has quite good performance, usually for such kind of tool, you won't be able to have it pressed anymore. For AB, for single thread, it is just about 20,000 CPS. And we don't have a lot of sponsorship. We don't have that expensive testing facilities. In order to do a distributive client server to do the test, we don't have that many servers in the laboratory. So how did we do that? We happen to have a research project using DPDK and Linux TCP IP stack combined. Then we have a unikernel application. Through this unikernel application, we implement a really simple HTTP client and server for our Vortex benchmark. The performance worked really well. For one core, it had around 50K CPS. For the whole server, basically 2 servers can complete the Vortex benchmark test. Next, I want to give a brief introduction over the process. This is the unikernel application. We have Linux kernel transferred into a static library. I have the link to the application. The whole idea comes from Linux kernel library project. This project was founded in 2010. Back in 2010, it was designed for a Haiku operating system to migrate Linux drivers. This project, it was under kernel 2.6. It was transcoded into static link laboratory. Of course, it had a long static age. What we do is to have LKL project migrated to up forward from 3.14 until Linux 3.x. In between, the idea mostly comes from RUMP. RUMP had sent an email to DPDK because they have a NetDSD protocol to run together with the application. So we feel very interested. We give a test run. We don't see the performance is good. At least it is even worse than Linux kernel. We are seeking for other things. We have NS3 DCE project. NS3 DCE had Linux network protocol stack separately and develop a dynamic SO, but it can deliver more things. For the thread, the memory, all of the implementation are replaced with user space implementation. We give it a test run as well. Of course, the performance is much better than RUMP. However, it is still not that optimal. Based on our test, SKL has the best performance. There are a lot of other issues. For NS3 DCE, they use Meloka to call the memory directly, so the management efficiency is much lower than Linux. Basically, for the memory module, it consumes around 20% of the performance. For the diagram from the bottom up, it achieves UL architecture module. Such a module, most of the code are using the general purpose generic architecture module. Of course, some of them are learned from SKL and copied something from user space Linux model. From DCE, there are also something. So this is the architecture. With such architecture, we will be able to have Linux kernel as transported to a Linux static library. We achieve the DPDK network driver. From this driver, we will be able to send all of the message on the top layer with TCP IP stack. We make only a few lines of modification. Including socket layer, you don't have to modify it at all. For system call, we just need to export the system call handle functions. On the right-hand side, we have socket callback. Socket callback, usually Linux use epoll to do the polling and the calling, but for such architecture, we use the socket callback functions directly, which also has call-in and call-out, etc. We have this callback directly transmitted to the upper layer, instead of calling for epoll API anymore. The whole architecture is the library. Regarding top-layer application, we can use the system call directly. We can also use socket callback. But for the top applications to be more smoothly migrated, we have additional layer of hijack layer. The hijack layer is using LD preload. The socket function will be hijacked. So basically, all of the parameters can be sent to the bottom layer directly to the socket function. Only with epoll, we have done some changes, taking advantage of socket callback instead of using the traditional epoll function. All of these in combination, the DPDK, Netcard, Linux, TCP stack, we have them run in the same process and have them banded to one CPU core. Of course, you may talk about what about multi-cores. Take NGS example. If we have multi-cores, then it is multi-thread. Each thread and process will have its own Linux TCP IP stack. And for the Linux kernel transcoding, the SMP is eradicated, so the transcoding will be a single core Linux drive, so everything else will be better performed.
Therefore, the unicore performance is, compared with the original Linux kernel, it's a little bit better. And next, here are some of the achievements we had. It's very simple from Ubuntu 14.04, and we didn't modify anything. For every request, we requested for the GIF, and you can see that in the original version in the Linux protocol station, when it reached hardcore, it doesn't have any improvement because the lock may use up 20% of the CPU, and with the lock UL, By binding the cores with each application, we can lead to a very linear scenario. Basically, in 2670, it can reach as high as the CPS of about 700,000. And next, let's talk about maintenance and operation. At UCloud, after development, it's only a small step of our work. At UCloud, we attach greater importance to providing service to the customers. Therefore, the operation and maintenance are even more important. About the use of DPDK, it's no exception. About maintenance and operation, we do have some difficulties once in a while about DPDK, and here are some examples from us. First is about CPU usage. It's usually a bit low because it's always polling. So it looks like the CPU usage is always 100%. However, our maintenance and operation team does not understand the workload of the system. So how do we scale up its capacity and how to send alert and so on? Then we have to do a calculation. For every round of polling, we look at how many packets we received and then calculate how many cycles it took to process them. And if we didn't get any packets, then this round of polling was wasted. Otherwise, it was effective. All the effective cycles were added together, and we can calculate its percentage in the total cycles, and that is the workload of the system. And then we can change the current work frequency of the CPU as well as maximum frequency to get the real workload. And after working out the workload, we dynamically change the frequency of the CPU, not to save the utility bill, but because we think if the CPU is under very high workload, then it will not be very good for the stability of the whole server. We wanted to work in a stress-free environment. We reduce the frequency. That is, as I just described, we dynamically adjust the frequency of the CPU. However, as we deployed it on HP servers, something happened. The DPDK power module was based on Linux ACPI CPU frequency module. So about the HP server, by default, it had the PCC power module, power management module. So it had this error box set that you cannot set the power management. But I think the Intel engineers are very, very good. They told me go to the BIOS layer, change it to OS control mode, then you can switch off the HP power regulator. However, after I switched off the power regulator, it still didn't work because what came out next was the Intel power regulator. And then we went to the kernel and switched it off, and then finally we made it. We could now manage the power, and this is the biggest problem I ever had. There was only one network cable of the server. I mean, some of those some heritage data centers, they only have one cable. It will be rather difficult for them to add any cables, like they have to file an application and then add some switches, and next time if they are to expand the capacity again, they will have to do that over again. To ensure stability, our servers are located on different racks. So for this kind of heritage servers, what could we do? We finally used the SRIOV method. That is, we virtualized the cable into a PF and a VF. The PF is managed by Linux, so SSH can be allocated to this PF. And for VF, it is taken over by DPDK. However, something happened. VF could only use 2Q even though it was 82599, so we could only use 2 physical cores. But fortunately, after a few days of Google research, we found that if Linux RxGB driver was to be updated to 4.1.5, we could create 4 queues, which would be barely enough for our lowest end servers. And next, about troubleshooting. Many other colleagues mentioned troubleshooting. Actually, I used to in a WeChat group and chatted with other operation providers. They said they didn't like the DPDK applications, and the biggest problem for them was that all the tools they were familiar with could not be used, like TCP dump, ping, and NTR, and so on. They couldn't use any of the tools they were accustomed to. Because anyway, when you have a problem, if you cannot locate the problem immediately, it may lead to huge losses of the client. So here we didn't have any solution, but what we can do is dynamically configure dump conditions. We can use relay and IPE as well as overlay IP and so on to determine whether we want to dump a packet or not. We use the RT packet dump to dump it. It's hard to read, and if you want to analyze it afterwards, it will be difficult too. However, dump can be copied and pasted, and then you can use the Y-track and import it to Y-track, so you can look at it closely. But that's still too much hassle. When you have an emergency, you have to find the log, paste it somewhere, and then export it, and then import it. That's too much hassle. And another thing is that about the packet to be dumped, if we put it in the debug tab, then we can use TCP dump and these tools to analyze it. But you may lose some information in that process. For example, the physical port and so on. You may lose some of the information. Up to now, we haven't found a better way to do it, but fortunately, about DPDK 1607, they do have this, and I think we look forward to the new features that can really satisfy the needs of the grassroots maintenance engineers and operation engineers. That's all for my presentation actually. If you have any comments, any feedback, please feel free to talk with me during the Q&A. Now the floor is open to questions. I want to ask you about the power regulator. During your actual operation, did you have any problem? No, we prevented the problems. Because for DPDK, the CPU use is around 100%. And if you switch on the trouble mode, its frequency can go even higher. So, we really dare not let it run that way for a long time. We don't want things to run in such an environment. For our data center has about, our data center is more crowded than telecommunication data centers, and the servers we purchased are more diversified. There are more different brands. So we dare not rely on the servers that much. If we can reduce the frequency and reduce the heat, I think that's a very good prevention. So now, what is the greatest intensity? How many cores did you run? Well, the most intensive was like 20 cores. I mean, two 10-core CPUs. So did you think about activating just some of the cores to run DPDK? We do reserve 2 cores. Like if there's a 10-core server, we reserve 2 cores for OS and 8 for DPDK. But if you allocate the cores this way, then for Intel, if you switch on the toggle, then it will increase the frequency of DPDK. It doesn't change the heating so much. Okay, thank you. I have a question. When you achieve the workload balancer, do you have to trace the link here for every core? So how do you make sure that when you go and return, you get the same passage? So no, we do it in one directional way, only one direction. Okay, thank you. Hello, in your presentation, you mentioned that for Ubuntu, you also look at the multi-tenant and how does that correspond to the core, and how do you allocate the resources fairly? Well, for major clients, key accounts, we do have physical servers deployed for them, but there are some small businesses that they run on their servers. Think about it. The bandwidth is like 10 GB, but there are so many small businesses that are our clients, and their bandwidth is only like 10 or 20 megabytes, and we do have the conglomerate to put these small clients on. They sometimes, like if there's DDoS or anything, the big conglomerates of servers can resist those things more easily. But of course, we have the security team. They do have some prevention before our platform. And specific to each server, they run the applications. How do the applications correspond to the client? Like one process, one client, one unit, or how does that work? No. We have all the 8 cores, and they become it's a whole server, and the different servers form a conglomerate, and this conglomerate serves like hundreds of clients. Thank you. That is why it's easier with DPDK. If you use kernel, you will have to allocate the namespace for each user in order for them to use the same IP address. But if you use that by yourself, if you do that yourself in DPDK, it's easier. Like in Overlay, you can pick the user ID and then make the connections. May I ask one question, please? Do you have any plan to make it open source? Vortex. Yeah, when we first developed it, we discussed that. We did think about open source. But then, well, actually, I forgot to say this. Previously, the Linux protocol station was based on LKL, but after year 2010, LKL was never updated. But fortunately, right before I make this slideshow, I noticed that last year Intel activated the LKL development.
It's in the version of 0.6 already, and they are very active. So I do think that's very helpful because it is capable of having the native Linux stack to be used by DPDK. So I would like to specifically say thank you to Intel. So if no further questions, we will do a tea break. If you have any questions and feedback, you can have the question on the floor. Our Intel engineer will be there as well to receive some of your questions.